Hello everyone, my name is Hongzheng Tian. I'm from the EECS department of University of California, Irvine. I'm so glad to give a presentation on LATTE 2023 about PyAIE, a Python-based compiler framework for Versal ACAP platforms. Firstly, let me introduce some basic aspects about Versal ACAP. Modern computing platforms are moving towards heterogeneous architectures in order to satisfy the current demand for various computation-intensive applications. Xilinx released the Versal ACAP platforms, which is a heterogeneous adaptive compute acceleration platforms that is integrate scalar engines, adaptive engines, and AI engines. This platform provides powerful heterogeneous acceleration capabilities. AI engines in Versal platforms are configured as a two-dimensional array of VLIW processes. The array includes 400, which is 8 by 50 AI engine tiles, with each tile including a AIE core and data memory and different interconnections to communicate with other neighboring AI engine tiles. The AI engines are programmed using C and C++. Xilinx tools will translate this source code into VLIW instructions and then deploy them on the AI engine tiles. However, even though we have those tools provided by Xilinx, it is still very hard to program a working project on Versal ACAP platforms because all the code of components including the AIE array, host program on the scalar engine, and the adaptive engine for data movers are required to be manually programmed and deployed on the Versal ACAP platforms. Besides, currently, most domain-specific applications use Python as their primary programming language. But as we introduced before, Versal ACAP-based acceleration projects must be written in a C and C++ with low-level intrinsics in order to take advantage of the Versal ACAP platforms. Consequently, a significant amount of inefficiency will be introduced, and results a longer development cycle. To solve these issues, we propose PyAIE, a Python-based programming framework specially targeting AI engines in the Versal ACAP. PyAIE allows users to focus on algorithm-level designs without knowledge of the underlying lower-level details. PyAIE automatically translates Python code into optimized AI engine standard C and C++ code along with generating configuration script files, thereby completing the entire AI engine-based system design. Here is an example structure for the input Python code, and inside this code, there are two main parts. Firstly, this part is the main function of the code. First of all, this part will initialize the inputs and outputs, and then call the top function by using Python decorator pylog. Here, the pylog is a previous work, which is an algorithm-centric Python-based programming and synthesis flow that targets FPGA, but our work can be treated as an extension of pylog that targeting the Versal ACAP platforms. This part is the top function, which is the input to the PyAIE compiling flow. The blue part is the main part of the top function. It will initialize the sub-inputs and outputs, and then call the three sub-functions. Those three functions will be targeted to different devices, such as the PL, AI engines, and the host CPU. The top source code will be sent to the Python built-in abstract syntax tree module, and then generate the top AST. The top AST will be passed to the PyAIE front-end analyzer and then generate the three sub-ASTs of each sub-function. The three sub-ASTs of these three sub-functions will be sent to the pylog front-end, whereas the main function with the data flow informations will be sent to the PyAIE code generator directly. This pylog front-end then parses this sub-AST of each function and then generates the pylog IR of each sub-function. This IRs has been optimized to target different devices. PyAIE optimizer then parses this IR and optimizes it with Versal ACAP programming intrinsics, and then transfers them to the PyAIE code generator. The PyAIE code generator generates different types of C code as well as some configuration files and make files by utilizing the Ninja template. When the code generation is finished, PyAIE runtime will take over and call the Xilinx Vitis tools to synthesize, implement, and deploy the subfunctions into different devices, and then it will feed the board with the input files from Python main function, and then transfer the output files back to the user's platform. And finally, there are two main aspects of our future works. For the Python-based compiler, we will further optimize the generic data-intensive tensor and optimize the system generation in the current PyAIE flow. And we will closely integrate the Pylog and PyAIE so that we can perform PL-AIE co-design and generate optimal PL accelerations. And then for the Versal ACAP platforms, we will further explore various communication options provided by AIE and improve the resources allocation algorithms, especially in the case where multiple functions shared the AIE resources. And lastly, we will include more AIE APIs into PLIR to support wider range of Python functions on AIE. That's all for all my presentation. Thank you for your listening.